Hiya! So we're going to be continuing the continuous uniform distribution. And one of the things we saw last time was that we have this as our probability distribution. So we have this kind of formula for the probability distribution. And we saw the expected value is this kind of formula, which made sense, right? Because this is just the average. And what we're going to do is we're going to try to standardize this by scaling our interval. Instead of being a to b, we're basically going to do something that we did at the beginning where we just standardize it to be from 0 to 1. And the reason this is nice, so this standardization, this rescaling is called the standard continuous uniform distribution. And it's basically just the continuous uniform distribution on 0, 1. So we'll see in a minute why it's super nice to have this. Well, actually, we can kind of see the super nice properties right away, right? So this means a is equal to, this means that a is equal to 0 and b is equal to 1. What this means is if I were to take my probabilities, we'll do this, c and d. Remember, this is just d minus c over b minus a. Well, b minus a is just 1, so we just get d minus c. So much more simple, we don't really have to worry about that at all. How about expected value? Well, expected value, this was, remember, just a plus b over 2. Well, a plus b is just 1, so we just get 1/2. So these are just much nicer things to kind of work with, and there's less things we kind of have to do. So how do we actually rescale? So say I have a continuous uniform distribution. How do I move into those standard uniform distribution land? How do I go from one distribution to another? So basically what we're going to do is we're just going to write a formula to get from one to another. So first we're going to let x be continuous uniform distribution. So let x, I guess I didn't write this down. X is continuous uniform. And basically what we're going to do is we're going to take a and b. So here we have x is defined on a and b. So the first thing we need to do is move a down to 1, and then we need to move b, or down to 0, sorry, and then b needs to move to 1. So basically we need to divide everything, or subtract everything by a. So I need to subtract by a, and then I need to divide by b minus a. In order to kind of make everything be what we want, right? So this will give me 0, and this will give me 1, right? A minus a is 0, b minus a divided by b minus a is equal to 1. So in other words, what we're going to do is we take our random variable x. What did we do? We subtracted a, so we subtracted a first, so we'll do minus a, and then we divided by b minus a. So we'll divide by b minus a. And that's it. So basically what this gives us is that x is just equal to, I can bring the b minus a over, so b minus a times u plus a. And that's it. So how does this help? Where's the kind of niceness in this? Well, we already know expected value of x. So in this case, I guess I should use u, since we're using u here. So let me put u's here so it's a little less confusing later on. So here's a u, here's a u. I guess I should write a little thing. There we go. So if I do the expected value of x, this is the expected value of a plus b minus a u. And this stuff, we already know kind of what to do, right? We can just bring out the a. We can bring out the b minus a, and we're left with e of u. Now here, technically, I already calculated 1/2. But if we really wanted, I can just calculate this integral, which is much, much nicer, right? because what I would have is what's my f of x? My f of x, remember, is 1 over b minus a in between ax there, otherwise. So my b is 1, my a is 0. So here I actually have 1. This is 0 to 1. This is for uniform, standard, uniform, continuous. Standard continuous uniform. Okay, let me rewrite this. Standard continuous uniform. Right. Okay. So this is just 1. So in other words, my function is much more nicer. I go from 0 to 1 of x times 1 dx. Now this should be a lot easier for people to solve if you want to solve the integral, because we just get x squared over 2 from 0 to 1. So we get a plus b minus a, just 1/2, right? Solving this, we just get, so here I would do 2a over 2 plus b, that was not a plus b minus a. So it's just a plus b over 2, which is what we had before. So it's basically just making this integral a nicer integral to do. And this method might not seem like, okay, like what are we actually gaining from this? But this is actually really helpful when we consider, for example, now let's try getting the standard variation. Now the standard variation, we would have to do x cubed, etc. In this case, I guess technically the easy part is our function is easy. But we can theoretically use this, we're going to use this idea later on to do more complicated things, which is why I'm introducing it now. So let's actually do the same thing with variance. So here, let's look up e of u squared. So this is not too bad, right? This is 0 to 1, x squared times 1 dx. So this is just x cubed over 3 from 0 to 1. And so this just gives me 1/3, right? So let's calculate var of x. This is just e of x squared minus e of x squared. Well, the second one we already know. Oh, actually, I'm doing this differently. Rewind. In my notes, I have a different way of doing this. We're going to do the var version. Technically, this way would work too, but I guess I chose to do it this way, so I'm going to do this way so I don't accidentally screw up u. So in this one, what we had seen is that this a part goes away, and then we square this one when we pull it out. So this we get b minus a squared, and we get var of u. And this is why I kind of I did it this way. B minus a squared, var of u is just e of u squared minus e of u squared. All right, so this is just b minus a squared. This is 1/3 from above. This e u we saw before is just 1/2, and we're squaring this. So we get b minus a squared, 1/3 minus 1/4. This is just, what is this? Let me see. This is 4, 12, 3, 12, so it's 1/12. So basically this is just b minus a squared over 12. So this is a much nicer way to kind of do things. It's a lot less work in essence than trying to do the entire integral if you wanted. Obviously this case, like I said earlier, it's not that difficult. You could do the integral, but we'll see, especially with the next example, that something like this might be a nicer way to do things than trying to compute the thing by hand. So I will see you in the next video where we will talk about the normal distribution. So I'll see you then.